Well, hi. Here is I've done a data collection for you, and you'll be able to see the first play data on a online Google Sheet. So we've already used a first play before in Lab 4, right? When you drop the ball on it and try to calculate the coefficient of restitution. So we're using the same method, and I was standing on a first plate, and I did a counter movement jump without arm swing and with arm swing. So these two column represents different movement. The first column is counter movement jump without arm swing, and this one is a counter movement jump with arm swing. I was jumping on it, and you should be pretty familiar with how to deal with force plate data, right? You imagine you can expect there will be like 2,000 or 3,000 data points, but you'll never you'll never be panicked about it. You know how to deal with it. So in this video, I will demonstrate how to calculate for without arm swing, and I'll find acceleration, velocity, and displacement, and try to plot it out. And then your homework will be to do the same thing before this data set with arm swing using the same method and to generate the same graph. I explained the assignment at the last video, but that's basically you need to do for this lab. So should be pretty easy. So let's do it. I'll do without arm swing, and I'll select the whole column and then copy and then paste on my Excel. Okay, so you should be able to see that. And let's see, there are how many data points? Around 3,000, I remember. Yeah, 3,500. And we can take a look at how it looks like. We can graph it out. So I do insert and line plot. And so the force looks like this. And it's standing still, descending phase, ascending phase, and then takeoff here. Flight phase. And then I went back to the force plate. So it's pretty similar as the graph we've seen before, right? Like this one. Sorry. This one. So you can see the force, like the descending phase represents here, ascending phase represents here, and then flight phase represents here. Okay, but how do we deal with this force? First, we need to translate into net force, right? So this is ground reaction force. We need to minus my body weight, so you'll get the net force. So if ground reaction force is equal to my body weight, the net force will be 0 here. And then negative means the ground reaction force cannot support my body weight, so it comes to negative. And then positive will be when ground reaction force is higher than my body weight. So the first thing I want to do is to minus my body weight. So I'll tell you that my body weight equals to 72 kilograms. But that's in Newton, right? So we need to get 72 times 9.8. To get 705.6. Okay, so for this column, we're doing net force equals to ground reaction force minus body weight. Okay, so I'll do the first one will be equal to A4 minus 72 times 9.8 parenthesis. Okay, so we get like pretty close to 0, but it's not perfect because the voice play has some offset, but that should be fine. Okay, so you get net voice here. We can plot it out again to see how it looks like when we make it in net voice. You can see it pretty much looks okay, right? The net voice is pretty approximately 0, then going down and going up. The shape didn't change, but the value changed. Okay, that's good. All right, so now we get net force. What we do next? We want to get acceleration, right? And acceleration would be force divided by mass. So we do acceleration equals to force divided by mass, right? And we're using net force here. So that'll be V4, right? Divide by mass. And for mass, we're using kilograms. But for force, we use Newton. So that's different. Okay, you get it? And double click on the black cross. You'll get it done for all the numbers here. No. Doesn't work. Okay, that's fine. I'll drag it down. It'll take some time. Sorry. Okay, got it. Nice. Wait, what's going on here? Okay, so when you drag it, you can see the function here. So it'll be V4 divided by 72. Here will be V5 divided by 72. V6 divided by 72. Okay. So we got acceleration now, and we can plot it out to see how it looks like. Same method. You can see, well, basically, it's the same as a trend of force, right? So because we just divide by body mass, the trend won't be affected, but the scale will be affected. You can see the acceleration, maximum acceleration will be 15, around 15 here. Okay, so now we get acceleration. Next, we want to get velocity. But how do we get velocity? You can take a look at this graph at the left. So each data point, the y value is the acceleration right now. You want to get the area below this line to get velocity. Okay, so first we need to calculate the trapezoid area for each one. So this line and this lines will be the value here because that represents y value, which is acceleration. But how about time? We know the force is collected in 1200 hertz. That means we'll get 1200 data point in 1 second. That means the time interval between two consecutive points will be 1 over 12,000. Okay, I'll put it in the function here to make it clear. So for here, we're calculating trapezoid area. So we need this one plus this one times time divided by 2. And because two data points forms one area, so these two data points will give us one area. That's why I go down one block. And then these two value will give us one area. Okay, so I want to calculate trapezoid area, which is equal to D4 plus D5, right? So that's 2 y value on this graph. And then I will multiply by the height. The height is time interval between these two data points, which is 1 over 1200, right? That's the height here. And then I want to divide by 2, but it's easier to multiply by 0.5. Enter. You get a trapezoid area here. And then when I drag it down one block, that'll be the trapezoid area for the second 2 consecutive points. Then I drag it down again. This value will be the trapezoid area here. Okay, then we need a trapezoid area for everyone. Now it works. Okay, but we know velocity will be the accumulation of all the trapezoid area before it, right? So the velocity here will be the area before this data point. So you need to accumulate all the trapezoid area together to get the velocity at this point. And then velocity at this point will be the accumulation of all the trapezoid area before it. So we need to use a sum. So here it will be velocity. And the first data point would be equal to sum and from E5 to whatever you want. So we use E5 to E5. But we want to keep E5 here. So we use money sign. And I click enter. That'll be the sum from this block to this block. So it's the same as this block. If I drag it down, you can see this block means the sum from E5 to E6. So that's a summation from this block and this block. So when we put money sign here, that'll keep it the same. If I remove it, that'll be E6 to E6. That'll change along the number here. But if we put money sign, that'll fix it there. So another example would be, drag it down. You can see that'll be E5 to E7. Okay, so you get velocity at each data point, right? And now we can try to plot it out and see how it looks like. Okay, so you can see that's the velocity. Initially, we have no velocity, and then it goes to descending phase, where velocity is going down. And then there's a transition from negative to positive, which means, if you remember, that should be the lowest point of your position. And then we go up. At the highest point, that's your takeoff velocity. It should be the highest. And then, after taking off, the gravity is bringing your velocity down until 0. That means you have your transition from positive velocity to negative velocity. That means you should be at the highest point here when the velocity is 0. And then you're going down. So that pretty much matches like what we expect to see, right? The graph looks pretty similar. That's good. That means we have really good calculation skill and really good force plate. Okay, so the second thing we want to get from velocity to displacement. And the concept is pretty much similar. We're using integration. But now the y value becomes velocity. And we use trapezoid area to find displacement. So again, we need a trapezoid area for velocity, which should be pretty similar, right? The first data plus the second data times the height divided by 2. So that'll be F5 plus F6. 5 plus f6, and then you times the height, which is the time interval between these two data points, which is 1 over 1200, because that's our sampling rate of first play. We have 1200 data points per second, so one interval will be 1 over 1200. Then we divide by 2. That'll be the trapezoid area. Okay, and you go down, drag it down here. I don't know why I cannot do it. 5, 6, 6, 7, and 7, 8. Okay. I need to drag it down again. Don't fall asleep, please. Okay, we are here. That's nice. Okay, I believe the number will show up later. Yeah, here it comes. Okay, sorry for the delay. Then we're going to accumulate all the trapezoid area to get the displacement at each data point. So we use, if you remember, we use sum function. We need to fix the first block. So we put money sign before it. That'll be money H and money 6 until H6. Okay, and then we drag 1 down. That'll be from H6 add to H7. Then from H6 to H8. So that'll be all the accumulated trapezoid area before that data point. Okay, and we'll get it down. That'll be the whole column represents the displacement. Alright, and then we can graph it out to see how it looks like. Alright, you can see the displacement looks pretty reasonable, right? So your center of mass is going down here and then going up. That's your highest point, and then you're going back to the first plate. And if we plot velocity together, that'll give you a better sense. So we're putting velocity together here. So you can see when velocity goes to 0, that correlates with the lowest point of your displacement. And because the velocity is transition from negative to positive, that's why it's 0 here. It's from negative to positive. And then when you get the highest velocity, that's your taking off place. And then after takeoff, your position continue to go up until the highest point, which correlates to 0 velocity, because the velocity is transition from positive to negative. That's why it's 0 here. And then it goes back to the first plate here. Okay, so our graph pretty much correlates with what we expect, right? And that's how you're going to calculate for another data set, which is what arms win. Okay, I hope you guys remember how we calculated. The first thing, we need to make it the net force. So we minus my body weight. And my body weight is 72. But for force, you need to multiply by 9.8 to make it Newton. And here, I use A4 minus my body weight. So that will be the net force here. And then for acceleration, we use force divided by mass. And because my mass is 72, you need to use kilogram at mass. So we use B4 divided by 72, which make the net force become acceleration. And then we want to transit acceleration to velocity. So we need to calculate each trapezoid area first in this column. So this value is a trapezoid area between these two values. And this is a trapezoid area between these two values. So this column is a trapezoid area for each trapezoid. And then we use sum function to add all the trapezoid areas together. And remember to put a money sign before it, so it'll fix the first block until the block you want. So it's from E5 to E5, from E5 to E6, from E5 to E7. And that's the velocity you get. Again, we want to transit velocity to displacement, and the method is pretty similar. We find each trapezoid area first, and then we accumulate them together to find displacement. Okay, I hope you guys enjoy the Excel sheet, and I probably put all these data on the Google Drive, so in case you forgot how to do it. Okay, I'll explain the assignment in the next clip. I'll see you guys later.